So we had some technical challenges, but I think it's fixed, so we can start. Welcome for joining me. This session we're going to talk about relevant search results. And I have a few examples, and I'm going to present these examples with Elasticsearch. It's kind of Elasticsearch oriented, but I think most of the things that I discuss you can also use in other search engines. When people think about search, they think about Google. That's what most people do. I use Google a lot as well, and I also like to Google my name. So this is me, Jettro Coenradie. I'm working for Luminous. If you want to find out more about what I do in my professional career, you can check my LinkedIn profile. If you want to know what I'm doing when having fun besides work, then you can check my GitHub profile, because there are all the projects that I do in my spare time, and sometimes even projects I do during work. You can also follow me on Twitter, and this is the company blog where I post most of the articles that I write about mostly Elasticsearch, but also other things that I find interesting. So we're going to talk about search. I use a sample application that I created myself, and it's an index. I hope it starts. Well, I just continue talking and hope that it will work, or else we'll just do it without this part of the demo and the other part will work. It's an application where I index the top 500 albums of the Rolling Stone top 500. So it's 500 music albums in there, and the idea is that you can search through the albums. It works. If I search for war, you can find a number of the albums that are from the Rolling Stone top 500. You can filter on, for instance, the artist, or you can filter on the label that published the album. Of course, you can enter other. If you're more into love than into war, then you can type other terms, and you can also look for artists immediately, which is interesting if you look for U2, that you will also find other artists. Well, that's actually the reason why this talk is important, because this is what relevant results are all about. It's not only finding some documents, but it's also presenting documents that are relevant to the user of the system. So, what are relevant search results? If you find the term relevant in Wikipedia, then it will say something like, something directly related, connected, or pertinent to a topic. So imagine you're thinking about searching for an album of U2, you would type in U2, U2 would be your topic, and then we're going to look for things that are related to that topic. And we found in the example that it could be Radiohead, for instance, because they might be influenced by U2, which is in their description. When talking about relevancy, there's two important parts what you need to think about when presenting results. The first one is precision. And precision means that you want to make sure that all the documents that you return, all the results, are relevant to the person that is searching. So we don't want to give results that are not interesting for the user that is looking for albums or documents. At the other side, we have recall. What we also don't want is that if something is interesting, we don't want it to hide it. So we want to present as many documents that are anyhow relevant to the user of the system, but this kind of contradicts to we only want to present the relevant items, but you also want to send as many as possible. So there is a trade-off there. So if we put that in a drawing, in a chart, we could say the number of documents on the horizontal scale and the relevance on the vertical scale. We would have a good recall if we are on the right, low right. And then we return as many documents as possible, and we're kind of sure that all the documents that are slightly relevant, that are returned to the user. But what if we need the high precision? So we don't want like 2,000 documents, we want to have only documents that are really relevant. And there's the trade-off there. So what do? What we can do is we calculate a score. With the score, we can return the items in a certain order, Therefore, we still return all the documents, so we have a good recall. But because the top documents are the ones with a high score, so they should have a high relevance, so the first few documents are also the ones that have a high precision. That's when we talk about ranked results. Ranked content based on the needs of your users. So you need to understand what the user is looking for. You need to understand what content you have in your search repository, and then you have to present back the most relevant documents first to the user. But we cannot search anything if we don't have anything to search for. So we first have to have content. If you have a number of pieces of text, you first need to explain the search engine what the features are that are in that text. What can he look for? So imagine you have this piece of content where the top, okay, computer, Radiohead is an artist. You could distill a number of features from this. So the first line would be the title, the second would be the artist, creation year, label, information, and finally the list rank. This is what we can explain to the search engine. These are the features you can use to select documents. But it's just like selecting. So how can we help the search engine to determine which one are more relevant? This is what we do with signals. With signals, we help the search engine to rank the content in the order that would, as we expect it to be, most relevant for the user. And a number of examples of signals. The first one is an easy one, just like filter on all the albums from the label Capital. The second one could be that we think that recent albums are more important than older albums. That could also be a signal. We could also say that if you look up this term that you're searching for and we find it in the title field, then that document becomes more important than if we find it in the information field. That's another signal. And we could also say, like, this is a bit vague because it's the word ranked again, but ranked in this case is meaning that ranked in the top 500. So the number 1 is more important than the number 200. So it doesn't have to do with the ranking in the search engine, it's ranking in the top 500. But also if we don't provide these signals, we also want the search engine to be able to give order to the documents. And the search engine has a mechanism for that, and that is calculating a score. So it has a mechanism, an algorithm to calculate a score based on what you search for and what is actually in the document. One of the things that you will often hear in this area is TF-IDF. This is a known term. Everybody knows what it is? Well, I see some heads nodding, so I'll explain. The TF stands for term frequency. What would that mean is that if in a field that you're searching for, the term is multiple times in there, it becomes more important. So if the field contains the term twice or 3 times, it's more important than if it's in there just 1 time. The inverse document frequency is more like a penalty. If the term you're looking for is in almost all the documents of your database, then that term in itself is less important. So if you were looking for 2 terms, and one of the terms is just in 2 or 3 documents, and the other term is like in 500 documents, then most likely that term is less important. And those 2 together give the search engine a way to at least do something with the scoring. Well, if you go to Elasticsearch, it's slightly more complicated. It has some other factors as well that influence the score, but for now, these are the most important ones. So now we have this database, we have this content in there, we know about the features of all the documents, but how does search itself work? How can we now search through these documents? Imagine we have this question. Find all all albums from the 70s that go about war, that contain the term war. We could do this in Java. Java 8, streaming API, it's nice, you can add filters. So in the first part we filter on the year, the period, the from and the to, and in the second line we filter on the information that it should contain the term and then return all the ones that are left. Is this clear? Also for non-Java, everybody Java programmers here? Most of it? I know from you that you're not a Java programmer, but you can read this as well. Yeah. It's not that hard. This is the last piece of Java I show you, so if you don't like Java, then you can stay. So this is all the documents. We have the features on the left, the title, information year, and all the others. We apply the filter, which is the 70s. In this case, the returning set is a filtered set of documents. And the next bit is we query. So we query for the term that we entered, in this case war, and we look in one field called information. And then we have ranked documents if we have a search engine. This was not really what we did in Java, because in Java we just filtered. There's no way that some score calculation is being done here. So maybe we should think about something else, because there's no scoring in here, no ranking. There's no lowercasing of terms. There's no correction for typos. There's nothing like stemming or synonyms. Of course, we can program this ourselves. Some of them are not even that hard. Lowercasing is not that hard. But there are better alternatives, and that's what we call the search engine. Well, Elasticsearch is an example. We also have Solar, which is, well, similar, not the same, but similar, and there are some commercial alternatives as well. But let's get back to the question. So this would be the biggest part of the query you would need in Elasticsearch. It would start with a bool query. And a bool query has a few elements. One of them is the must, and in there is a match query. We search for the term war on the field information, and the next bit is a filter where you can recognize the 70s again. This is the query way of doing it. There's two important differences, two important aspects of this query that I've shown you. The first one is the query context. The query context determines how well the document matches what you're looking for. So it calculates a score. This is where the relevancy comes in part. So it will check the fields, it will check if it's in multiple fields maybe. This is where you can play around with. This is where you can influence the order in which the documents are returned. The other part is the filter context. The filter content doesn't really tell us how well it matches, it just tells us if it matches. It is a Boolean response. So if you go back to the 70s, in the 70s, a document was released in the 70s or not. It was not a bit released in the 70s. Well, you could change that, of course, if you would say, like, yeah, it was released over a period of time, and part of that time was released within the 70s. Okay, but we're not there. That's not what we're doing. So in this case, if we go back to the query, the bottom part is the filter context. So no score is calculated for that part. It just filters out the documents that we are going to create a score for, and then it looks up all these documents and calculates a score based on the query context. Yeah? So what I've shown in the Java example is that we just have a collection with all the documents, and then we do a loop and we go through all the documents and we check it ourselves. Well, if you have 500 documents, that's fine. That works fast, no problem at all. Put everything in memory and you have no problems. When you have a bigger database, like 1 million documents or 100 million or even more, it is maybe a bit of a performance problem if you would go through all the documents and check if there is a term in there. So we use another mechanism, and that mechanism is called the inverted index. Who reads books? Technical books mostly. Do you do it on paper, electronically? Yeah, both? Okay, if you do it electronically, you probably use Ctrl F or Command F and find a term if you're looking for that term. But if you're still, well, if you're like me, 40 plus, and you still like to read on paper, old-fashioned, then there is this handy thing called the legenda in the end, the index. And then what you can do there is you go to the back, you look up a term, and then you find the page where that term is at. But this is an inverted index. So we don't go through all the documents, we go through all the terms. So we have a term that we're looking for, we look up that term, and then there is an index that tells us if you found this term, then you should look in this page to find information about it. This is how the inverted index works. But how do we get to these terms? I didn't tell anything about that. We just have text, we have features, but these features are just fields. So I have the album title, I have the artist, but this is text, it's not terms. So how do we come from text to terms? Well, this is an example. This is in one of the information fields in one of the documents. And we would like to go from this sentence, yes, to these terms. These are the terms that will in the end be in the inverted index pointing to that specific document. How does it work? In Elasticsearch, there's 3 steps. We have the character filter, we have the tokenizer, and we have token filters. So how would that work? In the character filter, we filter out stuff. We could filter out HTML elements that are not important, strange characters in this case. We can configure this, which character filter to use. In the next step, we took away these red things, and we keep the other part of the sentence. But now we want to make tokens out of this sentence that we can in the end put into the index. So these are the tokens. In this case we use the standard tokenizer that just mostly uses white space and dots and a few other things. But in the end, after this tokenizer, we would have this amount of tokens or terms. In the final step, we can apply token filters. In this step, we can do something with the tokens. So it could be a lowercase filter, for instance. The lowercase filter would take out all the capitals that are in here, and it would make new terms without the capital characters. Then in a following step, we could apply a stop words filter. Stop words are things like these small words that, well, don't really have a lot of meaning, so we can just take them out because almost all documents contain these items. If I would search for the word in, I think all 500 documents would be there. It doesn't help me get better documents, so I'll take them out. And then for me, in the final step, which is, I wouldn't say this is a good example that you should do, because wind and storm, they might not really be related, but what I did is I applied a synonym filter that would, if you would find the word wind in there, it would also add to the inverted index the word storm. Well, there are other ways of using synonyms as well, but this is just one example, but it is an example to show you in which part you would do this. So in the end, these are the terms that we would put in our inverted index, the bottom row. Now, we talked about features. So we had the album, we had the information, we talked about the process, how to come from text to terms. But I think you noticed that you can configure it. It's not one way of doing it. You can tell Elasticsearch or the other search engine how it should handle each field. So maybe the album title should be taken care of in a different way than the information block. And that's where we get the mapping. Is it viewable in the back? Yeah, because the letters are kind of small. This is a mapping that you can provide to Elasticsearch. So if you create an index in which we store the documents, you provide a mapping. And the example I show here is the information field. We say it's of type text. Type text would mean for Elasticsearch to just analyze it in a standard way, which is almost similar to the one I've shown, except for the stop words. Another one is the keyword. The keyword is different because it doesn't create tokens out of the text. It just uses the complete text as a single token. And this is, if you notice, the field I used it in is the label field. So each label that you apply, so if you apply the label to an album, it will not try to tokenize it. If it's 2 or 3 words in that label, I don't really care. I just want it to be one single term. So I use the keyword. And then the final bit would be the album. This is a specific type in Elasticsearch, what we call the multi-value type. The multi-field type, sorry. It's multi-field. So the default field is of type keyword for album, but there is another field parameter. In this case, we call it analyze, so this is a name. I could have called it anything I would like, it's just a name. And I apply for this analyzed field the text. So now this field album has actually two different ways how it's being handled by Elasticsearch. So I can use them both. I can use them as a keyword, but I can also search on it. Okay, let's start searching. This is a client Elasticsearch provides. It's part of Kibana. It's called Sense. Oh, I think it's Console nowadays. It was Sense. And I want to use it to show you a little bit of the queries. I did put this nice. I think I need to change the font a bit. Is this viewable in the back? Too small, I think. I'll just put it a little bit bigger. Oh, it's already on 18. 24. Is this better? Yeah? Okay, cool. So this is the most basic query that you can create. This is what we call the match all query. What you could also do, use this for is to determine the amount of documents in the index, but there's also a specific endpoint to that, which is called the count endpoint. The first part in this URL is the name of the index. So if I leave it out, it will just query all indexes, but I want to be specific in this index, so I use it in here. If you start using this, but you want to use curl, there is a way to copy this request as a curl request. But for now, I think this is good enough to show you the queries I want to show you. What we can also do is apply the match all query ourselves. So this is the same thing. There's no difference. It's just another way of writing it down, being more specific. If I write it like this, I tell Elasticsearch to use the match all query. In the other case, Elasticsearch just sees, hey, there's no query. Let's create the match all query. So it's the same thing. I already talked about the bool query, so let's add the bool query. This is the bool query, and the bool query comes with a part for the filter. So now we add a filter to the bool query. So this is the filter context. We can do a range query on the field here, 1970. So it's a GTE, which means greater than or equal to, smaller than or equal to. So in this case, I put this. And now we return all the documents. Oh, sorry, I thought, why don't I see documents? But it still uses the count endpoint. So now I see documents. So what you can see here is there's 186 documents matching this filter. And you can also see that there's no scoring. That's the reason, because we only apply a filter. And for a filter, scoring is not calculated. What I did not show you is if I would do this with a match all query, then all documents you would see have a scoring of 1. Because there's nothing to base a score upon, so it will always return 1. Okay, let's continue. The query was to also include a match query for the field information and lookup war. Now we have 4 hits. But we have more features than this. We had the album, the title, we had the artist, so there's more things we can search for. Then there is another query, which we call the multi-match. And now we can look up, for instance, the artist. As you can see, there's code completion here. But this is this is kind of small. It now shows 3 fields. It shows the artist field, the artist analyzed, and the artist grant. So this is a multi-field. The analyzed we already saw. The grant is something that we will use on later on. But I want to search on it, not filter. And for the searching part, I need to have the analyze variant, or else it will be just 1 token. And it doesn't have a number of tokens. So I need the analyzed version of this field. I still want to search in information, and I want to search in the album, which is the same thing. That's called the album analyzed. So what now happens, maybe I can just put it better like this, then you can see, it will now do a query, but it will query not 1 field, it will query all 3 fields. So let's apply it. We still see that there's just 4 documents. So it didn't change a lot. Actually, it didn't change at all. And the scoring is now here. Now you see that the score is not 0 anymore. It has actually calculated a score. Okay. Let's move on. What I mentioned is that you could also influence the score by providing a signal. One of the examples that we gave was making the title field, for instance, the album in this case, this is the title, more important than the others. So what you could do is, this is a way of boosting the title field, the album field. So what I'm just saying now here is that it would calculate a score for all the fields, but it would apply a multiplier with a factor of 10 to the score coming from the album analyzed field. So this way you can make the analyzed album field more important than the others. Now there is a trick that you can see how this works. If you really want to go into it into depth, there is an option called explain. And when you do the explain, you get an explanation, and the explanation will tell you how the score in the end is calculated. So this can help you figuring out what happens. At first it looks like, oh man, that's a lot, but if you come to look at it, you will see terms like term frequency again, inverse document frequency, you will see multiplications, you will additions, and if you find out how the query works, then it's pretty okay to follow the explanation. So yeah, you should just take some time to figure it out. If you're really into this topic, there is another blog post or even a video from me online that goes into depth into this area. Okay, now I've shown you that how you could say that the album title is more important, but we also mentioned something like we want to have an impact for the date of the album. So if it's more recent, we want it to be more important than if it's an old album. So let's get there and see what we can do in that area. I'll just start over. Rolling 500, the search endpoint. Oh. We again do a query, but now we do something called the function score query. And in the function score query, we store the bool query. And for now, let me just copy the multi-match. I don't have to type that again. And I leave out the filter part. So we only do the query part. So now we're back into all the albums, not only for the albums in the 70s. And then in these functions, we have a number of functions. One of them is the linear function. And this is the function where we influence the score ourselves. This is like what we call a decay function. So we do it on the field year, because this is the release date. And we would say like, okay, so everything, we're now living in 2017, so let's take this as the basis, and we would say that, yeah, well, scale it down, but I'm only interested in albums up to the 70s. So I want it down to 1980, for instance. The others I'm not interested in. So now what would happen is it would multiply the score, and it would be a great number to multiply it with if it's 2017, but it will approach 0 when we go to 1980. So if you go over 1980, the score will be 0, so it will never be on top. That's what this function score thing does. So in this case, we can help our users getting more out of the content to make the specifics, like the relevancy of their search query, more close to what they really need. Because I want only albums that are after the 70s. So I would run this query, and then it's a problem. So what did I do wrong? Anybody knows it? So the bool query needs additional information. It needs to know where to store it. So we had the match, and we had the filter part, and I left out the filter part, but I also left out the must. So now we have the must in there, and if I would now, I'm trying, if I can show you the explain true. see if we can find out what it works. This is the product of. And let's see if I can close this a bit. So here you now see the calculation at the bottom of the factor that is used to change the score. This is the decay function. So this, you can see that the explain function is actually quite useful. You can really follow along. Okay. But I promised you more, because I talked about synonyms, and there's no synonyms in here yet. What we have with synonyms is you have to tell Elasticsearch the synonyms it has. You have to apply it to a mapping structure. Well, it's a bit too much to show that as well, but believe me that you have to create your own analyzer, and then you apply that analyzer in your mapping to a specific field. So I have already done that. And what I now would like to do is that if you search for U2, that it would actually search for U2 in the other way, like the way we know the band is called. So if I'm going back to the query part, and I think I can reuse this one, U2, it will find not, it doesn't really find albums about U2, does it? I mean, close to you. Oh, let's leave out the explanation now. This is not what we want. So I go back, and this is a file which is called the synonyms file. And in here I can specify synonyms. If you look, there's the wind and storm part. Can I make it bigger? Yeah, I can. Okay, this is what I already showed in the example. So in this case, this means that if you apply the term wind, it will also add the term storm. But this is not really what I want, because I don't want to look up U2 this way. Oh, I have to use small. What I want is to replace this with this. So if I now look for U2 written out, I want it to look for the actual term U2. So I apply this in the filter file, and now I send this file, oops, wrong path. This is the reboot thing. Development. Give me a sec. It would be too bad not to show this. Gridshore. Yes. Okay. And now we try it again. And where is it? It doesn't work. There must be something like U2 in here. I think this is all the... No. Well, this is a good demo. This is what you get when you do live demos, then they fail. Sorry about this. I think it didn't really work. Let's blame it on the reboot for now. I mean, it's the reboot fault, not my fault, of course. Now, I had one other example. Oh, it's 3 minutes. Well, I have another example that I just briefly touch. I will not do the demo then. I will just mention it that you get the grasp, and then we have a few minutes left for questions. This is something called edge engrams. And edge engrams is what you can use if you want to do things like type help, so autocorrect or auto-suggest. It's used a lot. So if we would index the field, for instance, the artist Coldplay, with an edge engram, it will actually create all these terms. So if I would now search on the term C, it will already find, it could be able to find Coldplay. If I would type in cold, it will also find Coldplay. This is another way of enhancing your index to help users get a better experience and have more relevant results. I was already in the presentation. Okay, I think that was about it. Well, all the other links that I showed before, if you want them, look them up. I'm open for some questions, if you have.
Can you hear me? Yeah. I was wondering about the filters. Is it really applied in the order that you have displayed, or can you influence that so that you can maybe introduce a contextual filter?
Well, you can influence it by changing the order yourself. So it's the way you apply the filters, that's the order in which it will be applied as well.
So you don't have to lose necessarily, like by removing the codes, you don't have to lose the fact that Masters of War is actually a term that you may want to search together.
Yeah, well, the quotes is a bit different because that is a character filter. So that's always the first step. So if you don't want to lose the quotes, yeah, then you have to apply a different character filter.
Right, thanks.
Yeah.
Hi. Thanks for the presentation. It was a nice one.
You're welcome.
I'm curious that there might be instances wherein in the search results, some of the information are relevant, but we probably might not want to show that information. Maybe, confidential data.
Yeah.
For example, in a banking application. So what would be the best approach to in such scenarios?
Yeah, what I usually do is I add fields. So I add filter fields that are specific, so maybe with the role of the user that can see that information, and then in your query enhance it. So just apply the filter. We do that for a lot for security related, that not everybody can see it. Then we just apply a few additional filters by default, and that way you filter out the documents that you're not allowed to see. But yeah, you have to enhance the documents that's in the index. Yeah.
So does Elasticsearch provide any default option for masking such results?
Sorry?
Does Elasticsearch provide any default options for masking such kind of results? If you provide any filter, is it possible to mask any search result by default?
No, well, in the query you can limit the fields that you return, but there is a plugin in Elasticsearch, but it's commercial, which does apply a lot of security features. So but it's a commercial plugin.
All right, thank you.
Okay, you're welcome.
Hello, thank you for the presentation, really nice. I was wondering, is there a way to automatically generate a list of synonyms, or do you need to provide them manually all the time?
No, there's no automated way. So it's actually something that we're thinking about. That there are open source lists of synonyms, and the format is common. So it's a standard format. So it is possible to get one of these open source lists and just put it in, but you have to do it yourself. Yeah.
Okay, thanks.
First, thank you for the presentation. From your experience, it's not necessary to be a very objective answer, but Solar or Elastic? Well, just opinion, doesn't have to be right?
Yeah, that's a question that's asked a lot. There is about 4 years ago that I decided to switch from Solar to Elasticsearch. But it's not really honest, because I was working for the company of which Elasticsearch started. So yeah, I knew all the people from Elasticsearch in the beginning. So it's not a very technical or reason to make that switch. I don't do anything anymore with Solar. So my knowledge about Solar is like dated 4 or 5 years. So it wouldn't be fair to give you now that I would say Solar is better or Elasticsearch is better, because I predominantly know Elasticsearch. I don't know Solar a lot. So it wouldn't be fair.
Okay, thank you.
Okay. Okay, thank you.